Hey guys, welcome back to the third installment of two-dimensional collisions. Two billiard balls of equal mass move at right angles and meet at the origin of an XY coordinate system. Ball A is moving upward along the y-axis at 1.9 meter per second, and ball B is moving to the right along the x-axis with speed 3.6 meter per second. After the collision, assumed elastic, ball B is moving along the positive y-axis, see image below. What is the final direction of ball A and what are their two speeds? Okay, so in this problem, we want to solve this just like any other one. And we're given a picture, which is nice. We've got ball B coming in from the X, A from the going upwards. They collide, ball B goes upward initially. So I'll be honest, you might be inclined to say that A is going to go to the right. And it's okay if you say that, but you don't want to jump into the problem like that. I mean, it's a reasonable assumption. Keep that assumption in your head. When you do a problem like this, you want to estimate and assume that maybe it goes off on an angle. If it turns out that it does go horizontally, the math will show that. And if it doesn't go just horizontally, then it's a good thing you didn't assume that from the beginning. Okay, so assume it goes off at angle theta. Here is ball A, and it's moving at speed v2a. So we're going to solve this just like any other problem. We're going to start with the x direction first, as you saw in videos 128 and 129. Okay, so let's go ahead and jump into the x direction. We're going to do conservation of momentum. So p1x equals p2x. So in the x direction, initially only b has x movement. So it's going to be mb v1b. And after the collision, the only thing that could potentially have an x component is a. So it's going to be ma v2a, and we'll call it v2ax, right? Because technically this will have components. It'll have an x component and a y component. Okay. So let's make this problem a bit simpler. We're told that the billiard balls have equal mass. Okay, so if we have a mass A here, mass B is equal to M, mass A is equal to M. So if both of these are M, they're the same, they cancel out. So you're left with V1B equals V2AX. And we know V1B, it's 3.6 meter per second. Okay, so therefore V2AX is 3.6 meters per second. So that's good because we found one component of it already. Okay, for the V2. We found one component already for object A. Okay, so let's go ahead and jump into the y direction now, because that's always our next step. So in the y direction, we do p1y equals p2y. Initially in the y direction, only a is moving in the y, so we're going to do m v1a. Notice I didn't put ma because I recalled both of them have mass m. Equals, in the y direction, finally, a is going to have a component, assume, and b is going to have a component as well. So it's going to be m v2ay plus m v2by. Okay. Now the nice thing is mass appears in every single term, so you can cancel it out. After canceling it from every term, you're going to be left with v1a equals v2ay plus v2by. Okay. Now let's solve for v2ay because that's really what we're interested in here. So if you want to solve for that, bring the v2by to the left, so you get v1a minus v2by equals v2ay. Or if you want to write it with the v2ay on the left, it's going to be v1a minus v2b. And guess what? We know v1a, it's 1.9 meter per second, right? So v2ay is equal to 1.9 meter per second minus v2b. So we don't know v2b. That's actually something else we're trying to look for. But we've got an expression that's almost on the way there. So before you think that we've exhausted all options, we still have one more trick up our sleeve. Okay, so they move along the y-axis, ball B moves along the x-axis. We assume the collision to be elastic. Now remember, in an elastic collision, that means kinetic energy is conserved. So I'm just going to write that in here. Make sure you write that down too, because honestly it sticks in your long-term memory when you write stuff down. Okay, so kinetic energy is conserved, and that means I can make a statement of EK1 equals EK2. I'm going to go ahead and do that on a separate sheet here. Or let's just keep moving down actually. Okay, so because the collision's elastic, we can say EK1 equals EK2. Now remember, energy is a scalar quantity. It has nothing to do with directions. So you can just plug in your speeds as they are. You can plug it, yeah, so let's go ahead and do that. EK1 equals EK2. All right, so with the elastic collision, we've got the initial kinetic energy equal to the final. So initially, both objects are moving. Finally, both objects are moving. And we know the expression for kinetic energy is 1/2 mv squared. They all have the same mass, just different speeds. So 1/2 for mass A, mv1a squared. For mass B, 1/2 mv1b squared equals 1/2 mv2a squared plus 1/2 mv2b squared. Okay, so we're going to do some canceling now. Something that appears in every term. We've got a half appearing in every term and a mass. So half and mass disappear from every term. So you're left with an expression for speeds. So v1a squared plus v1b squared equals v2a squared plus v2b squared. Okay, now v1a, v1b we know. So let's go ahead and plug that in. So 1.9 meter per second squared plus 3.6 meter per second squared equals, and we don't know v2a or v2b, v2a squared plus v2b squared. When you square these two numbers, add them together, you are going to get 16.57 meters squared per second squared. Remember, the meter per seconds get squared equals v2a squared plus v2b squared. Okay, so we're kind of at an impasse again, right? Because we've got another expression with two unknowns, v2a, v2b. Now, check this out. Up here, we made an expression with v2ay and v2b. Honestly, v2ay is v2a, just that's one of the components. And while you might think, okay, that makes another unknown because you need to know the angle, you technically don't, because remember we solved for v2ax. We have one of the sides already, and this is how we're going to solve for it. So I'm going to look at the problem like this. v2a, assume this is v2a, this vector. You can break it up into the x component and the y component. v2ay, v2ax, right? Those meet at a right angle. Based on Pythagorean theorem, we can make the following expression. We can say that v2a squared is equal to v2ax squared plus v2ay squared. That is how you solve a right angle triangle without using the angles. Okay, v2ax we found to be 3.6 meter per second. So 3.6 meter per second, that gets squared, plus v2ay is 1.9 meter per second minus v2b. That's also getting squared. So, I mean, this number you just square, you get the value. So it's going to be 12.96 meters squared per second squared. When you expand this out, so you square it, you're going to get the following expression. 3.61 meters squared per second squared. Where am I? Okay, 3.61 meters squared per second squared minus 3.8 meter per second. That term is with v2b, and then plus v2b squared. So I know it looks long, but I mean, this is an expression we can use for v2a. So there it is right there. We're going to use that down here when I'm plugging in v2a squared, okay? Because now I have an expression for v2a in terms of v2b. Even if it's squared, that's okay. I can always handle the powers later. Okay, so now if I plug this thing into here, I'm going to get, okay, so we have our 16.52 meters squared per second squared equals v2a squared is this huge long blurb plus v2b squared. v2b squared, I'll just write like that. Okay, so plug in your v2a squared, so it's 12.96 meters squared per second squared plus 3.61 meters squared per second squared minus 3.8 meters per second v2b plus v2b squared. Okay, so getting a little bit long here, but that's okay. Honestly, this is not so bad. There's a lot of like terms you can combine here. For example, meters squared per second squared, meters squared per second squared. Okay, so if you add those two values together, you are going to get, in fact, 16.57. So you've got 16.57 on the left, and you're going to get 16.57 on the right. Okay, and then of course you've got your minus 3.8 meter per second V2B plus, and then you get V2B squared plus V2B squared. That's 2 V2B squared. Okay, so my 16.7s cancel. Imagine bringing that to the left and subtracting it. It would disappear. You're left with 0 equals negative 3.8 meter per second. V2B, your patience is much appreciated. This is a very long problem. Okay, so on the right track, almost there. So at this point, I have V2B in both expressions. Honestly, imagine factoring it out. Okay, so V2B, you factor that out, you're going to get negative 3.8 meter per second plus 2 V2B, and that's equal to 0. So either V2B equals 0, which it doesn't, because we know in the problem we're told ball B is moving in the positive y-axis after the collision. So V2B is not 0. Okay, otherwise, normally when you have an expression like this, you would say this equals 0 or this equals 0 and you solve. But we know V2B cannot equal 0, so this expression must equal 0. So therefore, if negative 3.8 meters per second minus, plus 2 V2B equals 0, bring the minus 3.8 meter per second to the left, making it positive. 3.8 meter per second equals 2 V2B. At this point you want to, sorry guys, at this point you want to divide both sides by 2. So in other words, you're going to get V2B is equal to 1.9 meters per second. Okay guys, so let's see. So far we found V2AX 3.6, V2B 1.9. So really what we need to do is find V2A, right? Because we have V2AX. So check this out for a moment. V2AY, based on our expression from earlier, V2AY is equal to 1.9 minus V2B, right? 1.9 minus V2B. Well, guess what, guys? I just found that V2B is 1.9 as well. If you do 1.9 minus 1.9, you're going to get 0. So V2AY is 0. So what does that mean? That means that object A is purely moving in the x direction. So our original assumption was right. It's only moving in the x. There's no y component, but it's a good thing to check. Always just assume it's moving on an angle so you don't mix anything up later. And if it happens to be that it's got 0 y component or 0 x component, that's okay. You can always work with that when the time comes. So if that's the case, therefore we can say that V2AX is V2A, which is 3.6 meters per second. So I know I've boxed a lot of things here, so let me try to make it clear what we're trying to find. We were looking for the final direction of ball A and the two speeds. So ball A is going in the positive x direction, so let's actually indicate that in positive x direction. All right, so here is one answer, V2A, and we found V2B. It's over here. We already know V2B was given to us that it's going up in the positive y direction. Wow, guys, so that's it for this video. I bet you were fully checked out now. So guys, I'm going to end the video there. Enjoy the rest of your day. Can't wait to see you guys tomorrow in video 131, Simple Harmonic Motion 1. What? Wait, who's back to school? Pumpkin pie recipe. Okay, I'll save that for Halloween. Guys, so that's it for this video. I hope you enjoyed it. If you did, be sure to smash that like button and subscribe to Physics in the Flesh so you never miss a video from me, which, by the way, I post every weekday at 12 noon. So be sure to be on my channel at that time. Guys, as always, if you missed my videos from the past, be sure to click over there on the right. You'll see some of my latest videos there. And other than that, guys, I hope you enjoy the rest of your day. Peace.